Hello everyone and welcome to this primer to chemical engineering calculations. In this video, we will be discussing units and dimensions as well as dimensional homogeneity in preparation for our upcoming lessons. The concepts discussed and reviewed here are very important as they will guide us throughout our journey into the world of chemical engineering calculations. So let's begin. As mentioned, the following is the outline of this video. We will be discussing measurements, units, conversion of units, and dimensional homogeneity. Let's begin with measurements. We divide all of our known quantities that are being measured in terms of two categories. That's the fundamental quantities and the derived quantities. For fundamental quantities, we have exactly 7 quantities. That is length, mass, time, electric current, temperature, luminous intensity, and the amount of substance. These 7 fundamental quantities, when combined with each other, will give us our derived quantities. Here are just some of the basic examples of derived quantities. For example, volume is derived from the fundamental quantity of length. Another example is the density. The density is derived coming from the fundamental quantity of mass and length. Speed is derived from length and time. Force is derived from length, mass, and time, and so on and so forth. So basically, any quantity that uses a combination of the fundamental quantities or a combination of fundamental plus another derived quantity is a derived quantity. The understanding of fundamental and derived quantities are important for us when considering what units to use or are we using the proper units for this quantity. We will talk about that a little bit later. For now, let us discuss units. The International System of Units or the SI system is the system of units used in the Philippines and in majority of the countries. We are using the SI system because of its simplicity in converting from one unit to the other, or its simplicity of representing very small or very large quantities. I have here shown the 7 fundamental quantities and their corresponding standard unit in the SI system. For length, we have meters. For mass, we have kilograms. For time, we have seconds. For electric current, we have amperes. For temperature, we have kelvins. For luminous intensity, we have candela. And for the amount of substance, we have moles. It is important that you remember what the standard units are for the fundamental quantities. We cannot say that grams is the standard SI unit of mass. That's because we need to use the kilograms. If you use grams in place of kilograms as the standard unit of mass, then we would have some problems when we are determining the units of the derived quantities stemming from mass, such as density, force, pressure, work, etc. So what I'm saying here is for us to arrive at specific units for derived quantities such as newtons, pascals, joules, watts, and other units, then we need to use a combination of the standard units of the fundamental quantities. Let us illustrate that with an example for the units of force. Force is defined as mass multiplied by the acceleration of an object. If we take a look at the standard SI units being used to represent these parameters, mass is represented in terms of kilograms, while acceleration is represented in terms of meters per second or meters per second squared. When we multiply kilograms with meter per second, we get the unit of newtons, symbolized by the capital letter N. With that, we can say that the standard SI unit of force is newtons. So force has a standard unit of newtons. If we use a combination of non-standard units, then we would arrive with a different answer. For example, if we use grams instead of kilograms for the units of mass, and we used centimeter per second in terms of meters per second squared for units of acceleration, you will not arrive with newtons. Instead, we would arrive with a different unit that we call a dyne. And we all know that 1 dyne is not equal to 1 newton. I hope this illustrates the importance of using standard units. Let's proceed. One of the main reasons why the SI system was preferred over much of the world is because of the ease in representing very large or very small measurements. In the SI system, we accomplish that with the use of prefixes. Prefixes are single letters that are attached to the beginning of a base SI unit to represent a multiplier for that unit. We have here a list of some of the most commonly used prefixes: giga, mega, kilo, centi, milli, micro, and nano. Of course, there are a lot more other prefixes. It's just that these are the most commonly used. We also have here their abbreviations or their representative letters that we need to attach to the beginning of the base unit and its multiplier. To illustrate the use of the prefixes, let us use the base unit for length, which is meters. The multiplier for the base unit meters is 10 raised to 0, so it's somewhere here. Meters, multiplier of 10 raised to 0, or that is equal to 1. When we want to represent a big value of length, such as when we have thousands or even hundreds of thousands of meters, we may want to represent that with a prefix instead of having too many zeros. For example, if we want to write 100,000 meters, for this large measurement, we can represent this as 100 kilometers. We used the prefix kilo with a symbol of small k, which means that we are attaching a multiplier of 10 raised to 3 or 1,000. This also works the other way if we want to represent a very small value of length, such as when we are talking of cells or even atoms. Let's say, for example, that we have a dust particle which measures 0.000001 meters. We can avoid writing many zeros and risk having a mistake by simply applying one of the smaller prefixes. For example, we can write this as 0.001 millimeters. We simply attach the prefix milli, represented by the small letter m, which means that we are attaching a multiplier of 10 raised to negative 3 or 1 over 1,000. We can even further simplify the representation by writing this as 1 micrometer. We attached the prefix micro, represented by the small Greek letter mu, which means that we are attaching a multiplier of 10 raised to negative 6 or 1 over 1 million. As you can see, we eliminated the use of so many zeros just to represent the decimal place in the base unit of meters. Instead, we simply attached a prefix, and that simplifies our measurements. That is the rationale behind the use of SI prefixes. In the English system of measurements, we cannot use prefixes to represent small fractions or parts of their base units. And that is one of the biggest disadvantages of the English system of units. Speaking of, let us compare the units used for the measurement of length for the English system of units and the SI system. You would see here why the use of prefixes greatly simplifies the use of such units. Let us first consider the units of length in the English system. We have inches, foot, yard, and mile. These are arranged in an increasing order. For the SI system, we have micrometers, millimeters, meters, and kilometers. Let us take a look at our conversion factors between these units. If we want to convert inches to foot or feet, we would have to say that 1 foot is equal to 12 inches. If we want to convert feet to yards, we would say that 1 yard is equal to 3 feet. And if you want to convert from yards to miles, we say that 1 mile is equal to 1,760 yards. In contrast, for the SI system, if we want to convert from micrometers to millimeters, the conversion is 1 millimeter is equal to 1,000 micrometers. For the next step, if we want to convert from millimeters to meters, we say that 1 meter is equal to 1,000 millimeters. And finally, if we want to convert from meters to kilometers, 1 kilometer is equal to 1,000 meters. From this example, it is obvious that the conversions for the SI units are simpler because in between prefixes, usually they are multiples of 1,000, meaning that the next larger measurement is simply 1,000 of the previous smaller measurement. For the English system, at least in the units of length, we cannot see the same pattern. The conversion factor is different every step of the way. This leads to more memorization and more rooms for error. The bottom line is the SI system of units along with its prefixes are greatly simplifying the way on how we represent measurements. Of course, you still need to learn the skill of converting between English to SI units or even in between English units, because in the real world, we have to be flexible and we have to understand every system of units. Now, let's talk about the conversion of units. We want to develop our skill of converting between SI units, between English units, and between SI and English units. This allows us to be truly flexible in analyzing problems that are using a mix of units. In some instances, it could be unavoidable because the measuring devices can only give a measurement for one specific unit, be it either English or an SI unit. In this lesson, I will be pointing out the use of the unit factor method, which is also known as dimensional analysis, in order for us to grasp the process of converting from one unit to the other. This method is also useful not only for converting units, but also for other things like stoichiometry and ensuring that terms are dimensionally homogeneous. Here are some of the most common conversion factors that we might encounter. Of course, this is not a complete list. I am just illustrating some of the most common ones. We have 1 inch is equal to 2.54 centimeters, 1 milliliter is equal to 1 cubic centimeter, 1 hectare is equal to 10,000 square meters, 1 gallon, this is US gallon, is equal to 231 cubic inches, 1 kilogram is equal to 2.2 pounds approximately, 1 minute is equal to 60 seconds, and 1 hour is equal to 60 minutes. We will be using some of this for our examples. First example, let us convert 12.43 meters to inches. Here is our solution in the form of a dimensional analysis. We always start with the given, which is 12.43 meters, and we end up with what is required, which is the value in inches. And you see that for dimensional analysis, we are simply using factors, which comprises of a numerator and a denominator, in order for us to easily see to what units are we converting. The first factor here is the conversion from meters to centimeters. Our given is in meters, so it's quite natural that for the first factor, the unit of meters is in the denominator, such that the unit of meters from our given and the meter in our factor would cancel out. If you take a look at the second factor, this now concerns with the conversion from centimeters to inches. Earlier, we mentioned that 1 inch is equal to 2.54 centimeters. This factor is written in such a way that the centimeters is at the denominator of this factor, and that allows us to cancel the centimeters from the earlier factor. The only unit remaining in our conversion is inches, which is what we want. Upon the completion of the solution, we can now input this to our calculator. All of the terms in the numerator means to multiply, while all of the terms in the denominator means to divide. So we input this as 12.43 times 100 divided by 2.54. Of course, I am no longer including the multiplication with 1 or the division with 1. Our answer is 489.4 inches. And that is basically how we use dimensional analysis for the conversion of units. Let's take a look at another example. Let us convert 10,523 cubic inches to liters. In the previous example, we are converting between units of length. Now we are converting between units of volume. But one of the units has its origins from length units, that's the cubic inches, and the other unit is a pure volumetric unit, that is liters. Let us see how this is solved. Here is the solution. Again, we start with our given, which is 10,523 cubic inches here. And then we simply use several factors such that our final unit, which is the numerator of the final factor, is our desired unit. For our first factor, this is simply a conversion from inches to centimeters. However, you should notice that the entire factor is raised to the third power. The reason for that is our given is a volumetric unit, that is cubic inches, and that means that we can still use factors that uses length units. However, we have to raise them to the third power in order for them to be converted to volumetric units. The first factor can then be understood as 2.54 cubic centimeter is equal to 1 cubic inches. We simply distributed the exponent 3. As you can see, by doing so, we are now able to cancel the cubic inches units from our given and in the denominator of our first factor. If you take a look at the second factor, we are saying that 1 milliliter is equal to 1 cubic centimeter. This is now our conversion from a volumetric unit derived from a length unit to a pure volumetric unit. And as you can see, the cubic centimeter units from the numerator of the first factor cancels with the denominator of our second factor. For our final factor, we have to cancel milliliters. So we simply say that 1 liter is equal to 1,000 milliliters. With that, we can cancel milliliters, and you will be left with our desired unit, which is liters. We can now calculate. That is 10,523 cubic inches multiplied by 2.54 cube. Do not forget to raise that to 3. Finally, we divide this by 1,000 in order to have our result in liter. That is 172.44 liters. In this example, we have illustrated the conversion from a derived volumetric unit based on length to a pure volumetric unit. This skill will be very useful for your entire life as an engineer. So please don't forget this. For the final part of this video, let us discuss dimensional homogeneity. This is a very important topic that would guide you in your future problem-solving endeavors because you simply have to take a look at an equation and you can immediately determine what type of units do you need to expect from the answer. Dimensional homogeneity lies on the fact that for any equation to be true, the quantities on both sides of the equation should be equal. We are not just talking about the numerical values, but we are also talking about the units on both sides of the equation. This gives a whole new perspective into the age-old question, what is 1 plus 1? Of course, we all know that 1 plus 1 is equal to 2. But this is only true if all of the numbers here do not have units. We say that all of them are dimensionless. Let us examine what happens if one of these numbers has a unit. Let's say, for example, 1 meter plus 1 is equal to 2. Is this still an equality? The answer is no. This is no longer a valid equality. That is because even though the numerical side is true, the dimensional side is not true. Therefore, it's not a true equation. And that should be obvious by now because we cannot add 1 meter with 1 because we are not sure what is the unit of the other one. If we say that 1 meter is added with 1 foot, then the answer to that is not 2 meters. The worst thing is, what if the unit of the other one is not a unit of length? Can we add 1 meter with 1 second? Let's take a look at these two cases. Can we divide 8 meters by 2 seconds? Mathematically speaking, we can write that as 8 meters over 2 seconds. By doing very simple algebra, we can answer this right away. The answer is 4, and the unit is meters per second. This is a true equality because both the numerical equality and the dimensional equality on both sides of the equations is true. How about for the second one? Can we subtract 2 seconds from 8 meters? So we still have the same quantities, 8 meters and 2 seconds. We are just using a different operation. So let us write 8 meters minus 2 seconds. Can we have an answer to this? The answer is no. This is impossible because this is not dimensionally homogeneous. And that is the power of units. They can drastically alter the way on how we look at equalities. Because not only do we need to balance the numerical aspect, but we also have to balance the dimensional aspect. Let's take a look at a more concrete example. Consider the equation used to determine the gauge pressure. Is the equation dimensionally homogeneous? This is our equation. The gauge pressure is equal to density, rho, multiplied by acceleration due to gravity, g, multiplied by height, or h. Now, for this example, let us use the standard SI units for each of these following terms and let's see if this is dimensionally homogeneous. I am going to illustrate this in two ways. The first one is by the use of pure dimensions and the other by the use of units. Let's first use dimensions. If you remember at the top of the lesson, we have mentioned that we have 7 fundamental quantities. The derived quantities are based from the fundamental quantities, which means that we can boil down every derived quantity into a mixture of fundamental quantities. Case in point, if I represent the dimension of mass as m, length as L, and time as t. For example, height or h can be represented as L because its base dimension is length. G can be represented as L over t squared because its base dimension is length per time or time squared. And finally, density is represented as mass over length cube. This is simply mass over volume, and volume is represented as length cube. We say that these are the dimensions of the aforementioned variables. How about pressure? The base definition of pressure is this is the force applied per unit area. Force is then further broken down into mass multiplied by acceleration. Therefore, pressure can be broken down into the dimensions of mass multiplied by acceleration, that is length over time squared, divided by area or length squared. Simplifying this mixture of dimensions, we can say that this is mass over length over time squared. This is our representative dimensions for pressure. The true test of dimensional homogeneity is when the dimensions on the right-hand side of the equation is equal to the dimensions on the left-hand side of the equation. Let us see if that is true. On the left-hand side of the equation, we have pressure, and we have established that its dimensions are mass over length over time squared. Let us see if that is the same on the right-hand side of the equation. For density, that is mass over volume or L cube. For the acceleration due to gravity or G, that is length over time squared. And finally, for h or height, that is simply L. Let us simplify the right-hand side of the equation and see if they are equal. Again, on the left-hand side, we have mass over length over time squared. On the right-hand side, we can see the cancellation of the units. The two lengths in the numerator will cancel with the two lengths in the denominator. And that leaves us with mass over length over time squared. This is a true equality, which means the equation P is equal to rho times G times H is a dimensionally homogeneous equation. And that is the sign of a true equality. Now, if you are getting confused from using letters to represent dimensions such as mass, length, and time, you can do the second option, which is using standard SI units. Let me illustrate that for you. In the second approach, we simply use the standard units used to represent our parameters. For example, on the left-hand side of the equation, we have pressure, and the standard SI unit for pressure is pascals. On the right-hand side of the equation, we can also multiply the standard units of the following parameters. For density, the standard units are kilogram per cubic meters. For the acceleration due to gravity, we have meters per second or meters per second squared. And finally, for height, our standard unit is meters. Now, for us to be able to compare the two sides of this equation, we have to break down pascals into its basic units. Basically, we are breaking this down to kilograms, meters, and seconds. And we do that by representing pascals as newtons per square meters. And then newtons is further broken down to kilogram meters per second. Thereby, we are saying that 1 pascal is equivalent to 1 kilogram per meter per second. And this has to be equivalent to the simplification of the right-hand side of our equation. A simple cancellation of units would tell us that 2 meters in the numerator would cancel with 2 meters in the denominator, leaving us with kilogram per meter per second squared. And again, that is a true equality. You can use either of the two methods that I have discussed, either use the base dimensions or use the base units. Use the method that you are comfortable with. Anyway, they would give you the same results. Let us try another example. Suppose that the following relation is dimensionally homogeneous. The composition, the variable capital C, with units of kilograms per liter, varies with time t, unit seconds. According to the relation, C is equal to 0.03 times e raised to negative 2t. What should be the units of the constants 0.03 and 2? This is an application of the concept of dimensional homogeneity. By using that concept, we will be able to determine what are the units of each of the terms of this equation. The first assumption, which was given by the problem, is that this equation is dimensionally homogeneous, which means that the simplification of units on the right and left-hand side of the equations should be similar. Let us rewrite this equation in terms of its units. On the right-hand side of the equation, we have the variable C with units of kilograms per liter. This should be equal to the combination of units on the right-hand side of the equation. For the constant 0.03, we are trying to figure out what are its units, so let me first leave that as blank. And that is multiplied to e raised to negative 2 times t, but we don't know yet what is the units of the constant 2. So let us again leave that as blank. And the constant 2 is multiplied with time. The unit of time is seconds. Let's break this equation down into its basics. First, we will examine the exponential term, that is e raised to negative 2t. One useful thing to remember is that whenever you are encountering exponentials, natural logarithms, or trigonometric functions such as sine, cosine, tangent, etc., the collection of terms should be dimensionless. Let's say, for example, we have e raised to n. N here should be dimensionless. That means in our case, e raised to negative 2t, the collection of terms negative 2t must be dimensionless. So let us ask ourselves, what should be the unit of 2 such that when we multiply that with time, with units of seconds, their units would cancel out? Common sense would dictate that if we multiply a unit with its reciprocal, then that means that they would cancel each other out. So therefore, we simply multiply seconds with its reciprocal, 1 over second. And that means that the unit of 2 is 1 over second, or per second, or hertz. We can write this part of the equation as e raised to negative 2 per second multiplied by time. And that leaves our entire exponential term as dimensionless, or e raised to negative 2t is now dimensionless, or it does not have any unit. And we will be using that to figure out what is the unit of 0.03. The question now is, what should be the unit of 0.03 such that when you multiply it to e raised to negative 2t, the overall unit left would be kilograms per liter. Common sense dictates that we simply multiply kilograms per liter to a dimensionless quantity such that their product is also of a unit of kilograms per liter, right? That is absolutely correct, and we now deduced that the unit of 0.03 is kilograms per liter. We can write our entire equation as C with units of kilograms per liter is equal to 0.03 with units of kilograms per liter multiplied to e raised to negative 2 with units of per second multiplied to time with units of second. This is now a dimensionally homogeneous equation. And by using that concept, we were able to determine the units for 0.03 and for 2. Of course, from here on, we are still going to write equations the normal way, like this one, without including the units of the constants. This equation does not include the units of the constant and of the variables. However, I am just showing this to you so that you'll be aware that the constants in an equation also has a collection of units, and their units can tell us some things about the nature of those constants. Simply said, the units of these constants reveal a lot about the nature of the equation or what the equation and its constants are physically representing. That is the power of thinking with units and dimensions whenever you see equations. And we will be using that to our advantage, and we will definitely be using that mode of thinking for our next lessons. Throughout your chemical engineering journey, you will be encountering what we call dimensionless quantities. And our understanding of dimensional homogeneity also comes into play for these dimensionless quantities. These quantities are useful in simplifying complex equations in engineering. You can check if the following quantities are indeed dimensionless. That means that the left-hand side of the equation does not have any units because everything will cancel out. For example, we have the Reynolds number, which is defined as diameter multiplied by velocity multiplied by density divided by viscosity. In terms of standard SI units, diameter is in meters, velocity is in meters per second, density is in kilograms per cubic meters, and viscosity is in Pascal seconds. I will leave this up to you to simplify and see if this is really dimensionless. For the second one, we have the Prandtl number, PR, defined as Cp, or the heat capacity, multiplied by the viscosity, divided by the thermal conductivity. In standard SI units, Cp is joules per kilogram per Kelvin. Viscosity is Pascal seconds. And thermal conductivity is watts per meter per Kelvin. I am challenging you to prove that the Prandtl number is indeed dimensionless. Another example, which I will leave for you to solve, what should be the unit of H if the term H over Cp over G needs to be dimensionless? We have here the units of G and Cp expressed in terms of the standard units in the English system of units. G has a collection of units of pound mass per hour per square feet, and Cp has a collection of units of BTU per pound mass per degrees Fahrenheit. Using your knowledge of dimensional homogeneity, I want you to find for the combination of units for H that would make the entire H over Cp over G term to be dimensionless. If you want to verify if your answer is correct or not, you can simply message the instructor and send your solutions. And that marks the end of this video. Thank you for listening, and as always, keep safe.